We are jumping straight into a massive paper that's really shifting how we think about world models. It's called Hunyuan-GameCraft-2, Instruction Following Interactive Game World Model.
And this one is a big deal. It's really about the evolution from just making cool-looking video clips to actually building interactive simulated worlds. The main insight here is all about unification.
Unification of what, exactly?
Of control. So HG2 uses this massive 14 billion parameter mixture experts model that achieves what they call unified control. You can type in natural language, trigger an explosion, or use your keyboard and mouse, and the model it handles them in the same way.
So it's not just a video model anymore. It's a world simulator you can literally talk to. And I see the second big point here is solving temporal consistency.
Oh, absolutely vital. I mean, they tackled the classic crane short test long problem head on. Mm-hmm. The model uses some really advanced techniques like randomized long video tuning and this novel sync token mechanism.
A sync token, okay.
Yeah, and that's combined with the KV recache strategy. All of this just means it can maintain 3D and, temporal consistency over really long interactions.
And crucially, this is all happening in real time.
Yes. And that's the kicker. They did some serious engineering work optimizations like FB8 quantization, special attention kernels like Sage Attention, and they hit real-time generation at 16 FPS.
Wow.
And this combination of semantic control, long-term stability, and speed let them just set a new state-of-the-art on this brand new benchmark, InterBench, which is focused on causality.
Okay, let's unpack that. This idea of interaction. In, older game world models, when we said interaction, we mostly meant really simple inputs.
Right, like discrete low-level stuff.
Pressing WASD to move the camera, maybe clicking to jump. It was all very mechanical.
That's right. That was just simple state change. HG2's definition is a lot deeper. They formally define it as actions executed by an explicit agent that trigger state transitions in the environment with clear causal relationships and physical or logical validity.
So the model isn't just reacting to a button press. It has to understand the meaning and the consequence of the action.
Precisely. The causality is key. If you press D, it knows, okay, smoothly pan the camera to the right. But if you type a complex phrase like draw a torch, that's a whole different level.
It has to generate a new object from scratch, place it logically in the world.
And handle the whole visual transition from no torch to torch is now here, all from a high-level command.
So that unification you mentioned is treating a key press and a sentence as sort of equivalent action commands.
Exactly. They're just different flavors of action primitives that feed into the same core model. And this is what lets you have a world that responds not just to movement, but to you actively editing the content of the world with language.
And that's where the results get so wild. You see the demos where they just type appear yellow sport car or draw a knife and boom, it's there.
And then the user can immediately start moving around it. The car is instantly part of the 3D space, which means the model had to update its entire understanding of the scene from one instruction.
But the hard part, I imagine, is making that change stick, making it causally consistent.
Oh, absolutely. If you ask for a car and then try to walk into it, the model can't just let you phase through it like a ghost. It needs to uphold the physical validity of that new object.
Yeah.
That's a huge demand on its internal understanding of geometry.
Okay, so to do that, you need the right data. But it's a known problem that just scraping internet videos, well, it doesn't give you the causal labels you need. How did they solve that?
They started by being really strict. They created a filter for what they even consider interactive video data. It had to have one of three properties.
Okay.
First, a significant state transition, so a door opening, not just a door sitting there. Second, subject emergence or interaction, an agent appears or, actively does something. And third, a scene shift or evolution, like the weather changing. If it's just a static shot, it's out.
So they set the rules, but I'm guessing the sheer volume of that kind of data is still pretty low?
Exactly. So that's where their automated synthetic pipeline comes in. And this is really clever. They didn't just generate random videos. They focused on injecting causal intent.
How do you synthesize cause and effect?
By focusing on the start and end states. Their first method was the start-end frame strategy.
Defining two specific frames. Why?
This is for constrained scenes, things like environmental changes. Imagine you want to teach it to make it snow. You generate the start frame, a sunny day, and then you use an image editing model to generate the perfect end frame, that same scene but snowing.
Ah, I see. So you give it the before and after.
Right. And by forcing the model to generate the sequence between those two anchors, you guarantee the change is specific and stateful. It learns the action of make it snow.
Okay, that covers static things, but what about an actor moving or the camera panning? That's more dynamic.
That's their second method, the
Mhm.
first frame-driven strategy. For this, they just provide a compelling initial frame and let the model generate the sequence freely from there.
A bit more creative freedom.
A lot more. It's better for dynamic physics and motion, and it avoids the weird distortions you can get when you try to force a model into a really complex, predefined final state. This whole synthesis pipeline was crucial for bulking up their data set.
And the supervision that ties it all together is this dual captioning scheme. There's the standard caption, but the real magic for causality seems to be the interaction caption.
Yes, that's the secret sauce. The interaction caption forces the model to learn the action itself. They generate it by calculating the semantic difference, the delta, between the captions of two consecutive frames.
So the model is almost asking itself, what one thing changed between this moment and the next?
Exactly that. If one caption says a character next to a closed door, and the next says a character walking through an open door, the interaction caption becomes simply opening the door. It distills the action. So the model has to learn both what the scene looks like and what happened in it.
Okay, let's get into the architecture. The base is a 14 billion parameter mixture of experts diffusion model. So how do they actually inject both the keyboard movements and the freeform text prompts into that beast?
They unify the control signals before they ever hit the main model. So for the low-level stuff, the keyboard and mouse signals, discrete actions like W, A, S, D, are first translated into continuous camera control parameters.
So it's not seeing W key down, it's seeing a vector that means move forward by X units.
Precisely. And to encode those 3D camera movements, they use plucker embeddings.
Plucker embeddings, that's pretty specific.
It is. But think of it as a sort of specialized mathematical language for describing 3D geometry changes. Since moving a camera is all about shifting lines in 3D space, these embeddings are perfect for encoding that geometric information really efficiently as tokens.
Okay, that makes sense for the geometry side. But then for the high-level prompt-based interaction, the paper says they use a whole separate multimodal LLM first. Why the extra step? Why not just feed the prompt in directly?
It seems like an extra dependency, but it's a necessary one. They found that complex verbs, especially abstract ones like vanish or trigger an explosion, were just too vague for the main diffusion model, which is, focused on generating pixels.
So the MLLM acts as a kind of translator, a reasoning layer.
Exactly. It takes that abstract command, figures out the fine-grained details of the interaction, and basically enriches the text prompt before it gets to the diffusion network. It removes the ambiguity. This whole multi-stage training process is what aligns those semantic commands with what you actually see on screen.
Right. Which brings us to long horizon coherence. This feels like the final boss for any world model. How do you stop the world from just falling apart after a few minutes of interaction? What's the clever trick that stops it from forgetting where it started?
The main solution is this really elegant idea called the sync token.
The sync token.
Yeah. So in normal autoregressive generation, your memory, the KV cache, is finite. Early information eventually gets pushed out. But the most important piece of information you have is the very first frame. It defines the whole world, the coordinate system, everything.
It's the anchor for everything that comes after.
It is. So they designate that initial frame as a special sync token. And this token is never pushed out of the KV cache. It's always retained right at the beginning, acting like a permanent GPS anchor for the entire session.
That's brilliant. It literally prevents the model from drifting because it can always look back and see where it started. It keeps those plucker embeddings for the camera from losing their origin point.
That's exactly what it does. And on top of that, they use a training strategy called randomized extended long video tuning.
Okay, what does that add?
It's about making the model robust over different timescales. They'll generate really long sequences, say 1,000 frames, and then they sample smaller random chunks from inside that long sequence to train on.
And how do they make sure the model is learning the long-term feel of the world, not just matching single frames?
They use a special loss function, a distributional moment distance loss. Instead of just comparing pixel to pixel, this loss compares the statistical properties of the generated video chunk to the real one. It looks at things like motion distribution and texture consistency over the whole segment. This helps it avoid those tiny frame-by-frame errors that add up over time.
Okay, now, the speed. 16 FPS. How do you get that kind of real-time performance from a 14 billion parameter model? That's insane.
It's pure engineering acceleration, just optimization across the entire stack. They use FP8 quantization, which massively reduces the memory needed and speeds up the math.
Right.
They parallelize everything they can, and this is critical. They use optimized attention kernels, specifically sage attention.
Why a different attention kernel?
Because standard attention can be a real bottleneck in huge models. Sage attention is custom tailored for this architecture to just maximize how much data you can push through and cut down the latency. It's a huge part of hitting that 16 FPS number.
And when a user is switching actions really fast, from walking to suddenly typing a command, stability is kept by the KV recache mechanism.
Correct. When a new prompt comes in, you can't afford to recalculate the entire context from scratch. That would be way too slow. The KV recache mechanism just grabs the new prompt's embeddings and recomputes only the very last autoregressive block. It's a shortcut that keeps it fast while making sure the new action is grounded in the latest state of the world.
This kind of new capability really needs a new way to measure it. The paper argues that old metrics like FVD are just not enough anymore because they only measure visual quality, not causality.
Exactly. And that's why they introduced InterBench. We should care about it as researchers because it's a diagnostic tool. It lets you evaluate the core causal loop. If your model fails, InterBench tells you why. Did it misunderstand the prompt? Did the physics break down?
So walk us through a few of the critical dimensions it measures.
Okay, so the first and most basic one is the interaction trigger rate. Did the action you asked for even start? On this, HT2 got a nearly perfect 0.983. Then there's prompt video alignment, which is semantic accuracy. If you ask for a knife, does it give you a knife or does it get confused and draw a wrench?
Right, and then making sure the outcome is actually believable.
That's covered by two big ones. Interaction fluency, which penalizes things like flickering or objects teleporting around. And for a simulator, maybe the most important is object physics correctness. Does the model respect gravity? Do objects have structural integrity?
And finally, making sure the action actually has a lasting impact.
That's end-state consistency. If you open a door, the door better stay open until the end of the clip. It can't just flicker back to being closed. This proves the model actually updated its internal memory. And across the board, the results show HG2 just crushing the baselines, especially on things like physics correctness.
So what does all this mean in the bigger picture? The paper suggests it has this amazing ability to generalize to things it wasn't even trained on.
Right. And that ability implies that the model has learned the underlying grammar of interaction, not just memorized a bunch of assets. It's learned the pattern, initiate an action, propagate its effects, complete the state change.
It's learning the rules of a simulated world, not just how to paint a pretty picture.
That's the key distinction. The demos show it generating things like a dragon or someone taking out a phone, even if those specific complex actions weren't in the training set.
That's huge. But we do have to talk about the limitations. I mean, it's not perfect.
Oh, definitely not. Despite how clever the sync token is, that long-term memory problem is not fully solved. The paper is up front that semantic drift still starts to creep in, especially after about 500 frames.
Why is that, if the anchor is there?
Because the sync token only anchors the initial state. It's not a dynamic memory of everything that's happened since. If you add 10 new objects to the scene, the sync token doesn't help you remember all of them. We still don't have a true long-term memory mechanism for the whole world state.
And the complexity of the actions is still somewhat basic.
Yes. For now, the interactions are mostly single-step, immediate effect actions. It can't handle a complex plan like, go to the garage, get the key, then unlock the car. That kind of multi-stage reasoning is still the next major hurdle.
Still, Hunyuan-GameCraft-2 feels like a massive achievement. It's really pushing generative world models into the realm of being genuinely playable interactive environments.
It absolutely is. It's laying down the technical foundations for what they call playable worlds, and a proof that a couple of things are non-negotiable. You need meticulous data definition, and you need these specialized architectural tricks, like the sync token, to generate experiences that are actually grounded in causality.
It's a huge step toward giving users not just a video, but an editable, persistent reality. So our challenge to you, the listener, is this. Given that semantic drift still happens in these long rollouts, what kind of new memory mechanism, something beyond the finite KV cache or a simple sync token, could robustly maintain the world state over an arbitrarily long session? How could a system remember every single object and every change you make over, say, a 2-hour play session?